Hello and welcome. In today's session, we are going to go through transformations of all kinds from all different sorts, well, not that many, from different sorts of coordinate systems. We're going to go through the mathematical background of each transformation, and then we're going to have a demonstration of it in code, and then we're going to do it all from scratch, and then right at the end, we'll have a look at GLM, which is a popular library which does all these transformations for us. Okay, so I need to preface this session with a massive disclaimer, and that is that if you're learning OpenGL, 100% the number one best thing you can do is learn linear algebra. I'm going to be going through this, and I'm going to be going through it from scratch. I think it's going to be pretty good, but it's not physically possible for me to go through every aspect of matrices and vectors. That's just a lot. So learn math. The sooner you do it, the better it'll turn out. And there is a massive amount of resources online for free, Wikipedia, YouTube, and things. It's really important. But having gotten that out of the way, I'm going to look at matrices. The first sort of transform I'm going to look at is what's called a model transform. And the idea of a model transform is to map between what's called model space and world space. Now, what are those things? Well, let's say we make a person. Okay, here's my person. And this is currently like open in Blender or something, so we have a local coordinate system. There's the person, they're at the origin, we model them and stuff, and then we have the world, okay? But we might want to take this person and put them out somewhere else in the world so that their origin doesn't necessarily correspond to the origin of the world. They're at some different position, some different translation. We might want to put them somewhere, but also apply a rotation. It's another case. So what we're doing is the transformation that takes something from local space, from model space, and puts it out into the world with some sort of transformation applied. That is a model transform. Okay, so the simplest sort of transformation matrix is the identity. And the identity has the property that when we apply it to a vector, it does absolutely nothing. So here I've got my identity matrix, and I'm going to transform, like I'm going to hit this vector with the matrix transformation. Let's compute the result. Now note that we've got x, y, z and a 1 on the end, just like we were putting 1s on the end in our shaders in the previous sessions when we're setting GL position. But let's go through this, and then at a later point I'll explain it in this same video. So doing matrix multiplication, so to get the first row, first column, what we do is we take the first row dot product with the first column. So we have component by component, 1 times x plus 0 times y plus 0 times z plus 0 times 1. So we can see the result is just x. Then we do the same thing. So we have 0 times x, okay, plus 1 times y, so 0 plus y, and then plus 0 plus 0, okay. And we keep going. So we have 0 times x plus 0 times y, 1 times z. I know this seems a little silly, but when we go through this, we find that, yeah, this makes absolutely no difference. Take the vector, hit it with the transformation, we get, as a result, the exact same vector. Okay. Now, later on, when we, what am I thinking? Later on, when we put these things in memory, because we're going to do this from scratch, it's important to know how this stuff is stored. So let's say we have a matrix. Let's go A, something like that. We sort of need to flatten this out into an array structure. But then the question is, well, do we read this left to right, top to bottom, or do we read it top to bottom, left to right? Now, as it turns out, in OpenGL, it's expected that matrices will be stored in what's called column major order. So that would be sort of down, and then looping around to the top, and then back, and so on and so on. So again, if we were to write this out as an array of floats, it would be in this order. We would have A as the first entry, and then E, I, M, and then B, and then so on and so on. So when we get to the demonstrations, we'll be showing how this is done. But again, we basically go column by column. Now, super quickly, this is a little esoteric, but I think it is nice to demonstrate. And I've done this many times, but I'll do it again. So when we have like a 2x2 matrix and a vector, do that multiplication. It's a linear combination. So we have A times X plus B times Y. And then down here in the second row, we have C times X plus D times Y. That is a general 2x2 matrix vector thing. But let's actually, because here for each entry we have a sum of things, so let's take that out and decompose it as a sum of two vectors. And then each of those vectors has a common factor, so we can factor out that scalar. And then look at that. It's pretty similar. So it turns out that when we multiply a matrix by a vector, the result is a linear combination of the columns of the original matrix. We have something times the first column plus something times the second column. And the coefficients in that linear combination are the elements of the vector. And so we could think about this as a dot product, but it's also useful to think about it as a linear combination of the columns of the matrix. And I like to, I wasn't in the room, okay? When the decision was made to make OpenGL column major order, I wasn't involved in that decision. But if I were trying to guess, I imagine it's because columns are super important in matrices. Well, rows are as well, but in this instance, it's a case where the math can be very much sped up, because if you can multiply and add a bunch of columns in one go, which you can do on modern hardware, we better. Anyway, enough of my rambling. So, column major order, and the next transformation I want to look at is something called translation. And this is where I'm going to explain the importance of that extra 1 on the end of the vector. So the concept of translation is to basically pick up a point and shift it by a constant amount in each dimension. So if we have a point x, y, z, I want to send that to the point x plus something, y plus something else, z plus something else. Those numbers can be 0, no problem there. So what we do is, this is a translation matrix. Alrighty, so what I'm going to do is I'm going to form that linear combination in the matrix. So I say, okay, I have something that when I multiply it here, I end up with x plus a. So I want to have 1 times x plus 0 times y, because y isn't in here, plus 0 times z, and then plus a times 1. That's the point of this 1 here, is if we maintain this 1, then it can be used as a sort of dummy variable to add on constant amounts to the other components. So again, we can look here and say, okay, I want to have y plus b as my resultant. So I'll have 0 times x, 1 times y, 0 times z, plus b times 1. And then similarly, in the third row, we'll have 0 times x plus 0 times y plus 1 times z plus c times 1. And there we have it. And then finally, the last column is very simple. It's just 1 times 1. Okay, so that's all well and good. Let's actually jump into the code now and have a look at how we can implement this system. Alrighty, so here we are. We're going to apply translations. Now, just to verify that this is working, we can run this. This is from the start folder in the provided code. There we have it. It's up there. And what I want to do is I want to take all of this and I'm going to translate it a little bit to the right and a little bit down. Okay, but there's a little bit involved. So what I'm going to do is I'm just going to make a new file. And this is going to be for my math stuff. I'm going to call this linear algebras. Let's make a header file. This was an old joke back when I was studying for my first degree a long time ago. We had a study group. We called them the linear algebras. Right, so I'm going to need to define a few things. We're going to need to define a 4x4 matrix. It's really just a collection of 6 entries. And also going to define a vec3, a 3D vector. There we have it. And what I'm going to do is I'm going to make a function which produces a translation matrix. So we're going to return a 4x4 matrix. There we have it. Okay, excellent. So now what I'll do is I will just go ahead and make another file, and that will be the source file for this. We'll go ahead and include that header. And now we can, what am I thinking? We can define this function. All right, cool. So we need to make a 4x4 translation matrix. So first of all, we'll create that matrix. That will be returned in the end. We need to set the elements. So first of all, I'm going to zero everything out. So I'll say all right, so this will just blank everything out with zeros. And now I want the, let's produce the identity. So if we think about which elements are 1 in the identity, it's the top left, which is, what am I thinking? This is, but anyway, the top left, actually, you know what? I changed my mind. I changed my mind. What I want to do is I want to show the way these matrices are actually written in column major order. So I'm actually going to do this one by hand. Okay, so this is going to be the first column of the matrix, and that will be, if we read it down, just a 1 in the top of the column. So there we go, that's the first column. Just think of reading the matrix down like that. Now we'll go ahead and write the second column and the third. These will all be pretty similar. We're really forming, this is like we're forming a 3x3 identity. So we can see the 1 keeps moving down. Okay, great. So when we make the fourth column, it will be sort of similar to this. For this fourth column, these entries will be the entries of the translation, so the X, Y, Z component of the translation. Okay, there we have it. So that has formed our translation matrix. Great. So now I'm going to modify the CMake file to include that in the project, and then I'll use it in the main. Yeah, All right, so we'll go down to the CMake lists, and then we just need to add this in here. Okay, it looks good. And, well, I misspoke. There is a little bit more involved. Not heaps, but a little bit. If we look at the vertex shader here, we have, I like to think of it like, this is the data we get in, this is the data we get out, and then in addition to that, we also have what's called uniforms. Now, I know that I used a uniform in the last video, but they weren't a strong focus, so I'm going to put a bit of explanation in now. So think of a uniform as a global variable which is applied to a shader. So we run the shader, but at the same time we throw in custom data. That's pretty much how we can think about it. So we're going to take in a 4x4 matrix, and this mat4, this keyword is GLSL's keyword. Okay, so it has nothing to do with the fact that I called these mat4s and vec3s. This is just the naming convention that I chose for my library, just to keep things unified. But anyway, just bear that in mind. So this will be called model because it's the model transform. And what we'll do is we will take that vector and hit it with the model transform. There we go. Excellent. So now I'll just head back to the main file, and we'll just go through the usual stuff. So we'll need to include our library. Okay, so right, here we are in our main file, the main function here. I'm just going to do all this stuff in place, keep it sort of simple, because refactoring and all of that will be a focus of a future video. So I'll just go ahead and declare the position that I want. And I will use that position to generate the model transform. Okay, cool. So if we look at this, this is essentially going to shift everything a little bit to the right and about double that down. So it's going to go right and down. Okay, so we've got that, but right now this is just existing in RAM, in the CPU, in the program, and we want to get that stuff over to the graphics card. So what we've got is we've got a uniform here, but this is a variable which is defined in the shader. That's external to the program. So what I like to do is I like to query the location of that external variable and have it on store so I can use it anytime I want. In this case, we're just going to use it once, but you know, we could not. So these handles are all unsigned integers. I'm going to call it model location because it's the location of the model uniform on the GPU in the shader, and this is with GL get uniform location. We're getting the location of the thing on our shader, and its name is model. That will query that for us and return that handle. Okay, so having done that, the next thing we want to do is upload to that location. So that's done with GL uniform matrix for float vector, I want to say. Okay, no worries. So the arguments we get in here are the location we're uploading to, the number of matrices we're uploading, just one. The next parameter is whether those matrices should be transposed. That'll be false. That will always be false. And then the final argument is basically the pointer to the location, to the array that we're uploading. So in this case, we have that model matrix, and entries is the array which has all of the float values in it. So we can just pass that through, and it will read it off from that array and get the matrix in there. So I think that's it. I think that's all we need. So fingers crossed, we'll do a bit of debugging maybe. Oh, no, it worked. Okay, so as we can see, it's moved a little bit to the right and a little bit down. Okay, and just to check this, we can change this. So let's move it even further. Yep, that's what I expect. Let's move it up and to the left. Yes, it is up and to the left. Okay, excellent. Great. So I'm happy with that. We'll just, yeah, let's move on. Okay, so that's translation. We're just picking points up and we're shifting them. The next one I'm going to look at is rotation. So I'm going to do rotation around the Z-axis. So let's just look at the OpenGL coordinate system for a little bit. Okay, so this is our screen space. We have our Y running up and down. We have our X running left and right. And then we have our Z-axis going through the screen. If you imagine you're looking into the screen, that's the Z-axis. Okay, now here we have Y up is positive, X to the right is positive, and the question is, where is Z positive? Well, this is a little funky, this is a little weird, but it turns out, okay, take our right hand, curl our fingers from X to Y, our thumb is coming back at us. That's the right hand rule. So Z positive is actually behind the viewer. That's weird. So all the visible region we can see is actually in the negative region, but we'll actually deal with that later. This isn't really relevant to what I'm talking about. It's just priming. We're going to see this later. Okay, so rotation around the Z-axis. So what I'll do is, this is a great example of how to construct a general transformation, is let's have a look at what's happening to the basis vectors. So if we were to draw out, let's call this the I vector, 1, 0, 0, 0, because we're going in a 4D system. Okay, then if we were to look at the J vector, there we have it. Those are the original vectors. Now what we want to do is we want to take that system and hit it with a rotation around the Z-axis. So that will actually bring it around like this. And so let's rotate it a little bit. So this will be I hat, the image of I under that transformation. And then we'll do the same thing. So we'll rotate this around and this will be J hat. Okay, so rotating by an angle of theta. And we need to work out, okay, what are the components of I hat? Well, remember, this has a radius of 1. And so we can form that down into a right angled triangle. And with a right angled triangle, with an angle of theta, the horizontal component of this is the adjacent side of the right angled triangle. So that's 1 times cosine theta for the x. The vertical component is the opposite side of the triangle. So we have sine theta as our y. We have no z component and no w component. Think of it like that. Okay, now, this is where things get a little funky. For the j dash, we have the horizontal, the x component of j dash, basically, is the opposite side of the triangle. And with this orientation, it's actually pushing off into the negative x-axis, if that makes sense. And so we have negative sine theta. This is so important, I'm going to talk through it again. Okay, so with x we often think cosine, but here we can see this is the horizontal component, this is the x component of j dash, it's the opposite side of the right angled triangle, and so that's a sine, and it's pointing off into the negative x-axis, that's why that comes in. And then we have a look here, we have the vertical component is the adjacent side of the triangle, so that's cosine theta, and then no z and no w. Okay, so here's the idea. We have some matrix. The goal is to find A. That matrix is applied to another matrix which is built up of the basis vectors being, let's say, I, J, K, and I'm gonna call this L. We'll see why in a second. Basically, I want to form a 4x4 identity matrix, and that will produce the image vectors. Okay, so the basis vector I is just 1, 0, 0, 0. The basis vector j is there. Now the basis vector k is essentially just 1 in the Z, and the basis vector L is 1 in the W. Because we're dealing with a 4x4 system, we need 4-dimensional basis vectors. Okay, so what do we have? We have I dash. Now I dash is going to be cos theta, sine theta, 0, 0, because we've worked that out here. J dash will be negative sine theta, cos theta, just like that. Now K dash, if we have where we have the z-axis, we're rotating around the z-axis. The z-axis itself doesn't change under that transformation, and so that will be unchanged. And then similarly with the W, well, rotation doesn't really change that, so we'll just keep that there. Now, this is the trick. So we took the basis vectors, we worked out their image under the transformation, and then if we really inspect this, we see that this is A times the identity, which is the same thing as A. And so this matrix here is the matrix for the rotation around the z-axis. I would encourage you to draw some diagrams maybe and work out the rotations around other axes. For instance, around the x and y axis. But that information is available on Wikipedia as well. But anyway, so we got that. Let's have a look at that in action. Okay, so now let's have a look at applying some rotation to this. Again, we'll start with the library and we'll go from there. So we'll go to linear algebras, and then right up here what we want is another method. I'm just going to call this create. Excellent. So this will be a rotation around the z-axis, and as input we'll take the angle. Okay, great, and let's go ahead and define this. Okay, right. So we'll get back to that, but we're going to need a few extra things. One thing is we're going to need a math library so we can do sine and cosine. So we'll just go, include CMath, that'll do it. And then I also want to define pi. So I'm going to define a number called pi, and what is it? It's 3.14159. 62, I think. I used to have students who memorized so many digits of pi, and I just memorized 3.1514159, and they always said with a 62, so there we go, 62. Perfect. Doesn't really matter. I mean, the accuracy is tenfold for each digit you memorize, so it's diminishing returns, honestly. But let's get back to this. So we get this angle, and what I want to do is first of all convert that angle to radians. So I'll say angle equals the conversion factor is pi over 180 degrees. Excellent. Right, and I'm just going to, for quality of life, I'm going to just define a few pre-calculated values. There we go. Excellent. So just get cos and sine. This f on the end is just specifying that it's going to return a floating point value. Right, so if we read this column down, we have cosine and then sine, and the rest is zeros in the first column. Then in the second column, we had negative sine and cosine, and then zeros. And then the rest of this is fine. I'm just going to switch this over to zeros. Okay, excellent. That should be our rotation matrix. Cool. So let's go ahead and use that. So we'll just go off to the main, and we'll get rid of this model. We'll keep the quad position there. We might need it later. We'll get rid of this as well. We're actually going to be updating this every frame. So I'll just put that inside. Okay. And yeah, let's do this. So say mat4. And for the time, I'll go. There we go. That'll just basically query the system time. So we'll have something spinning around. So let's save that and give it a go. There we go. And as you can see, we're spinning around. Now, if we watch this very carefully, we'll see that it's not perfect. So when we come around here, we get squashed too far, basically. And what's happening is that all the quad knows is that it needs to fill the whole screen. So if the screen size changes as it rotates, the quad will just make sure it's filling the screen, and the aspect ratio is not equal, and so that's where the weirdness is coming into this. But yeah, there we have it. That's rotations. Nice to see. Okay, so we've had a look at a translation, which is putting something in a position, and we've had a look at a rotation, which is spinning it around. Now, clearly, objects are going to have both of these things together. So let's have a look at stacking those those translations together. So the way we multiply matrices, the way we apply transformations, is sort of we stack them onto the left. So let's say we perform a rotation first, and then we perform a translation. We are basically multiplying those matrices. It's, transformation 1 and then transformation 2. And then the goal here is to say what's a general matrix that represents this sort of thing. So let me just write this in. Okay, so that's a translation. And then we multiply in the rotation. Okay, now this is going to be a little strange because we're doing a full 4x4 matrix multiplication. Okay, so we have 1 times cosine, fair enough, plus 0 times sine, 0, a times 0. So what we've got is, this is just picking out the cosine, then everything else is zeroed out. So we just have cosine, and then we'll do the same thing here. So let me just talk through this again. We're working out the first row, first column in the resultant. So we take the first row, dot with the first column. What we want to do now is we want to work out the second row, first column. So we take the second row, dot with the first column. So we have 0, sine, 0, 0. Okay, now I want the third row, first column. So take the third row, dot with the first column. And as you'll see here, we have 0, plus 0, plus 0, plus 0. And same thing with the fourth. Now we bring it over here. We have the first row, second column. So first row, dot with the second column. That's negative sine. And then everything else here is zeroed out. And you may see a pattern. Anyway, let's keep going. So we have again, and now here we have the first row, third column. So first row, third column. That's 0, 0, 0, 0. If we were to keep doing this, we would get the following. Now we come to this one. This is where it's interesting. So we have the first row, fourth column. So 0 plus 0 plus 0 plus a times 1. And then again, all zeros plus b times 1, just like that. Now, this family of matrices are super interesting because they actually sort of compose together. So if we were to look at this matrix here, this component is really describing the translation. Actually, we probably shouldn't include the 1, but yeah, let's do that. Okay. Okay, so this last vec3 on the end here is the translation, and then this region here, this 3x3, is describing rotation. So when we have a matrix which is a composite like this, we have a rotation component and a translation component. This is what I call a geometric matrix because it has a meaning in it. It's not random. And the benefit of this is that these geometric matrices have very simple inverses. So in general, inverting a matrix is pretty tricky, at least computationally. It's an O(n) cubed operation. But if we have a matrix like this, then we get a closed form we get a very simple inverse for it. But anyway, let's dig into the code and have a look at this composite transformation. Alrighty, so we've got positions, we've got rotations. Let's bring them all together. This should be pretty straightforward. We'll just go to the header and we'll go, create model transform. And what we'll need is some position and some angle, just like that. Awesome, no worries. So we'll just go over to the linear algebras and take that method, that function. There we go, no worries. And what I'll do is, really, we're sort of smashing these two vectors together. So we have matrices. We have this matrix and this matrix. And remember, the upper 3 by 3 is rotation, so we don't need to worry about that. It's the fourth column which needs to change. And then again, over here, the upper 3 by 3 is rotation. That stays the same. It's this column which needs to change to include position. Okay, so we'll take that and just rename that translation to position. There we go. And it should be as simple as that. So what we can do now in order to use this is just go over to the main, and then right down here we have the quad position already set. We just need to bring in that rotation as well. So we'll go create model transform based on the quad position and the rotation angle. Done. Okay, let's give that a shot. And as you can see, we are shifted and rotating. Excellent. I'm happy with that. Okay, so that's really all we need to know about in terms of like putting things out there in the world. The next transformation I'm going to look at is what's called a view transformation. Now, a view transformation takes world space and transforms that into view space. Now, what is the benefit of that? Well, so far we've been doing the following. We've got some sort of quad, and it's here, and we're looking at it, and we're viewing it in the screen. That's great. But what we really want to do is, it's more common, at least, hey, your experience may be different to mine, but in my experience, it's more common to actually have Z as the up axis. Oops, there's our quad there. And we might want to sort of view it from some perspective. So imagine this. The question is, how do we get that into this form? I'll do another explanation of this in a second. But basically what we do is we shift things around. So we subtract the camera's position, and then we rotate opposite to the camera. So we have some sort of transformation like that. And this diagram looks bad, so I'll just do another quick mock-up of a different scenario. This isn't quite as mathematically accurate to what's happening with the Z being positive, negative, whatever, it's fine. So what we want to do is say we've got a box, for instance, we're looking at it from some position and perspective or something. Now, ultimately, what we want to do is we want some sort of transformation that will move the box to an orientation where it was as if it were being viewed by the camera like this. So just imagine taking the camera's frame of reference and aligning that with the axes. Now, I'm going to say this a bunch of different ways, but this is super important. The view transform is the inverse of the camera's model transform. Let me say that again. So imagine we have the camera here. This is it in model space. This is the camera in world space. Okay, so the camera has some sort of model transform that would put it out into the world. To get the world back into the camera's frame of reference, we do the opposite of that, and that's the view transform. So again, the view transform is the inverse of the camera's model transform. Another way to think about it, subtract the camera's position, rotate opposite to whatever rotation the camera has. Sort of like here I am in my room, if I turn to the left, I can be very solipsistic about it and imagine that I'm not moving and the world's actually spinning to the right, for instance. But okay, that's all well and good. That's fine. Then the question is, well, what's the camera's model transform? Well, the camera is a geometric matrix. It has a rotation component and a scale component. Here's our camera. It has a bunch of vectors. It has a forwards vector, a right vector, and an up vector. Now, the right vector we can think of as like that's what happens to the x-axis. So that's our I dash. That's our image of the x-axis. Our up vector is like the image of the y-axis. So after we hit the world with our view transform, the right, left and right of the screen should be lining up with the camera's right direction. The up and down of the screen should be lining up with the camera's up vector. And we have the forwards vector, which is the image of the, what am I thinking? The image of the z-axis. Okay. We also have what's called the I, that's the camera's position. So if we were to look at, we'll call this A, the camera's model vector. Okay. It's a geometric vector, so 0, 0, 0, 1. Okay. For the rotation component, that is, we have the I dash, that's the right. Then for the J dash, we have the up vector. And then for the K dash, we have the forwards vector. Okay, now, the translation component of the geometric vector, it's really just its position. So it's the X component of its I, the Y component, and the Z component. Okay, great. Excellent. Now, our goal is to find the inverse of this. So we want to find a matrix B such that when we stack it onto that matrix, it produces the identity. So I'm going to make a claim and then we'll investigate it. And my claim is that for this rotation component, this is orthonormal. And what I mean by that is that the dot product or the inner product of two vectors is either 0 or 1. It's 0 if the vectors are not the same, and it's 1 if they are the same. Another way to think about this is that the vectors have unit length. They have a length of 1, and they are completely orthogonal, completely perpendicular to each other. They have nothing in common, which you would imagine if you were to look at this coordinate system. Like you've got your 3 fingers, they are completely like no parallel components with each other, and they all have unit length. So because they're orthonormal, the inverse of this rotation component is the transpose of that 3 by 3. So that makes things a little simpler, and I'm actually going to investigate that claim. So what I'll do is I'll guess a form for the matrix. I'll take the transpose, so that first column of the 3 by 3 becomes the first row of the transposed 3 by 3, and then we have that. And I'm going to just put in some variables here because I don't know what these things are. We'll work them out later. And then I want to take the multiplication of that with the where are we? Okay, so back to the matrix multiplication. So remember, we want the first row, first column. So we take the dot product of the first row with the first column. Now see here that this a times 0 is going to be 0. So that the end component is not going to contribute anything. By the way, I'm not sure if I mention this, but I like to use angle brackets to denote inner products or dot products. Look up what a dot product is if you're unfamiliar with that. But yeah, we have right dot with right, and then here we'll go to the next row, so we'll have up dot with right. Remember the way I always have trouble thinking of how in detail I should go on the math here. But when you have two vectors and you're going x component times x component plus y component times y component plus z component times z component, that is an inner product or a dot product. So that's what these brackets are denoting. Anyway, so then we have the forwards dot with the right, and then here we're just going to have 0, 0, 0, 0. It's all zeros. Okay, great. Cool. So moving on. Now we're taking the dot of all these with the up vector. So we have the right dot with the up dot with itself, and then the forwards dot with the up. And then again we'll have, let's keep it going. Why spoil the fun yet? So we have right dot with the forwards, and same with the up. And then right on the end here, now this is a little funky. I'll admit this is a little weird. What I'm going to do is I'm going to take, okay, these first three components are forming a dot product, and then we'll bring in an extra term. So we could form these as new vectors and do like just dot products of 4x4 vectors, but I'm not going to do that. So we'll have, here we have the right vector dot with the I plus this last term, a times 1. And then here we'll have the up vector dot with the I plus b times 1. And then we'll have, and then what are we doing right here down at the end? We will have just one. So you have all zeros plus 1 times 1. Okay, now remember that these systems are orthonormal. And so everywhere where these vectors match, it's 1. And then everywhere they don't match, it's 0. Now here we can't make that assumption because the I is a position. That's not a rotation thing. That's not part of the orthonormal system. So we'll just have the same expression. But we do know that we want to produce the identity at the end. In other words, we want these three components to be 0, and so we can choose that A will be the negative dot product, and same with B and C. There we have it. Okay, so this has been a long one, but to put it all together, the view matrix will basically be I'm going to make a little bit of an adjustment here. So far so good, but when we come to the Z component, I'm going to flip that around and I'm going to make that Z negative. So instead of just this one, instead of forwards X, forwards Y, forwards Z, I'm going to apply a negative onto those to flip it around. And then instead of instead of the negative dot product, I'll just have the dot product. I'll flip the sign on that. But otherwise, that is it. That is the view transform. Okay, so now we want to view this from a different position. This part is going to be a little more involved because I'm going to need to make a few helper functions. So I'll start off and show the workflow. So we want some function which creates a 4x4 matrix, which is really looking from some position to some other position. Okay. Now, as a part of that, we're going to need to calculate dot products. So I'll declare a function for that. We're also going to need to be able to normalize vectors. And we're also going to need cross products. Now, the reason we need all of these things is that when we create this lookat matrix, as you saw in the theory part, we need to calculate the orthonormal basis of the camera. In other words, the forwards, right, and up vectors. Those need to be normalized, and they need to have, or they need to be orthogonal. So the way a cross product works is you take in two vectors, take the cross product, and the resultant is a third vector which is perpendicular to the other two vectors. Anyway, so what I'm going to do is I'm just going to copy all of this over. There we go. And I'm sort of going to go backwards here. So apologies for this, but for this cross product, I am going to copy paste. It's sort of it's not super bad, but it is slightly messy. So I got this from the Wikipedia article on vector cross product, but I mean, hey, it is what it is. Just think of it as it produces a third vector which is orthogonal to the other two input vectors. I mean, there's more about it, but I'm just going to leave it at that. Okay, the less said there, the better. Now, let's go with normalizing. Okay, so the basic idea is we want to work out the magnitude of the vector and then divide every component by its own magnitude. What's happening on this line is it turns out that when we take the dot product of a vector with itself, the result is the square of the magnitude. So get that result, take the square root of it, and there we have the magnitude. Excellent. So what we'll do is we'll now set each of the entries in the resultant by taking the input component and dividing it by the magnitude. And we'll do that for all components. Excellent. Then we'll just, return the normalized copy. Okay, great. Now for the dot product. So the dot product is actually exceedingly simple. All we do is we take the component-wise product of each of the terms and sum them up. Okay, there we have it. I'll just format this a little bit. But yeah, it's really just the sum element by element. Okay, great. No worries. Let's close that down. And now I finally want to create the lookat matrix. So what I'm going to do is I'm just going to use a vector that I call global up. There we go. That will just help us to create this orthonormal set. Now I'm going to make the fundamental vectors. And I'll start with the forwards vector. I'm going to shorten these names a little bit, so I'm going to call this F. Now the forwards vector is where the camera is looking, so that will really be the point we're looking at minus the point we're looking from. Great, and now we'll just go ahead and normalize that. Right, so now what I want to do is I want to produce the right vector, and I always love doing this exercise. I take the fingers of my right hand, I'm pointing them in front of me right now, so I'm looking forwards into my laptop screen, and then I go from forwards, curl them up. So we're going cross from forwards to up, just like that, and I see that my thumb is pointing in the right, so that's what I want to do. I want to take the cross of the forwards, and that's the purpose of this global up. Okay, no worries. Now I'll do the same process. So I'll do the same thing. Take my right hand, I want my thumb to be up, so my fingers are curling from my right side in the forwards direction. So we go from right to forwards, and by the right hand rule, that resultant will be up. Okay, excellent. So now we will go through the process of constructing that vector. So I'm actually going to just copy this. Okay, so think back to the theory that we went through. For the first column, we have the 0th component of all of these vectors. But just remembering that we need to flip that Z around. There we go. And it's the same for the other columns. Excellent. And then in the fourth column, we will take the dot product. So we'll say, all right, take of the right and our eye position, which is the point we're looking from. And remembering, of course, to flip the sign on the Z. Excellent. So, provided I did nothing wrong, that should be working. Okay, let's go ahead and implement that. Now we're going to need to switch over to the vertex shader because we've got a new matrix. So we'll declare a new uniform. I'll call that view, and we'll just multiply that in there. Excellent, great. So we'll go back to main, and I'm just going to go ahead and define a few things here. Okay, so what we were doing before is we were looking at a quad which was spinning around, and the quad was facing towards us because the z-axis was like the forwards and backwards axis. But now what we should see is that we'll be a little bit back and a little bit above the quad, and we'll be looking at the origin. So we'll be sort of looking down at a bit of the quad. Okay, so we'll go ahead and we'll query the location of that view transform in the shader. And let's go ahead and send that matrix in now because it's not going to change over the course of the program. So produce that view and upload it. Okay, so moment of truth. Let's find out if this is running. Yeah, excellent. So yeah, as you can see, we are basically, looking down on it. Yeah, and so, okay, if it wasn't for the translation, it wouldn't be shifted to the right. So yeah, and that's correct. That's correct. It is clipping it off a little bit, but that's for the next section. Alrighty, cool. Okay, so that's great and all, but you may have noticed that some of that quad was being clipped because it was a little too far away. So what happens is that we go ahead, we set up the vector, that the vertex that's come through, and then perspective division is performed. So the W component, after all the mapping and everything, the W component should be storing how far the vertex is away from the viewer. And then all the coordinates, all the components of the vertex are automatically divided by that. And it brings things that are further away, it brings them closer. So it's the job of the perspective transform to set that system up. So there's two major things we're after. Firstly, the W component should store the distance from the viewer. So I'll write that out. We want to have W component stores the distance, which is Z, I guess. And then after perspective division, visible vertices will be in the range -1 to 1. So I'll say visible vertices will be in the range -1 to 1. Okay, excellent. So that's what we're going to try to set up. So to start with, I'll just start with our view. Okay, so we have something like this. I'm never good at drawing these things. We have some sort of range. Now, we start with this range, and then perspective division occurs, and we want to sort of squash that space from this pyramid shape into a cube. So everything's in the range -1 to 1. Okay. So I'm just gonna deal a little bit. If we look at this side on, imagine this is our eye level going horizontally. This is our near distance, and this is our far distance. Now, here we have the y-axis, here we have the z-axis. Okay, so we have some sort of angle which describes our field of view. We take half of that angle, and that's the field of view sort of looking up, the other half is looking down, and this distance is our near. And so this height, at this point here, our height will be our near distance times tan of half of that distance, because this is the adjacent side, this is the opposite side, SOHCAHTOA. There we have it. Okay. But then the question is sort of what's the X range there? And it turns out the X range will be the maximum Y range times the aspect ratio. And that's super important because you'll also note that when we looked at demos previously, the aspect ratio wasn't really being taken into consideration. So when the screen is a lot wider than it is tall, we rotate a shape, it'll look sort of normal, but then when it rotates around this way, it'll actually stretch around and fill up the space. And that's not good. I'll stop rambling, but it's not good. So we just want to bear this in mind, is the maximum ranges that we have, because we want to divide by those later on. But anyway, I'm getting too far ahead of myself. Let's look at a simple side-on case. So here's our z-axis. As we go further away from the viewer, we have our visible range here. Let's put an N for near plane, an F for far plane, and here's our person that we made before. So projection. We'll take it sort of, we imagine drawing a line like that. There's our person mapped onto our near plane. That's what we see, basically. And I'm just going to put, they have some original Y, and they get mapped to some Y dash. Now, if we were to look at this triangle and this triangle, they are similar triangles, so they're in proportion. So we have Y dash over the near distance, and they're at some distance Z as well, is equal to Y over Z. And so we get that Y dash is equal to near times Y over Z. But then what we'll do for our purposes is we'll take just near times Y, because perspective division, if we correctly store the distance in the W component, we'll take care of that anyway. Right, and similarly, we get that X is equal to, X dash is equal to near times X. But then we need to take into account the Y maximum. So if we were to look at this case, we have now that Y dash is somewhere between, what is it? It's, I'm just going to write tan of theta on 2. So it's somewhere on that range. And then X dash will be somewhere on the range of, all right, A for aspect. Okay, so currently we're mapping it and it's on this range. So what we want to do is we want to take these results and then divide by, in this case, so we have ny over near times 10. So that comes out to y on 10. And then x dash will be divided by aspect times near times 10. And that comes out to x over aspect times 10. So this is ensuring that after we perform the perspective division, the points which are visible will be in the range -1 to 1. So I'll just write out what we have currently. Okay, so when we transform this vector through, the formula for x dash, it's really just x divided by that factor. The perspective division will be completed later. And then for the y, it's really y divided by tangent. Now z is a bit of a mystery, but let's look at the w component. For the w component, we want to store z in the end. So we'll go 0, 0, 1, 0. That will store the z component there. Now, for this thing here, I'm just going to go 0, 0, whoops, 0. I guess I'm already using A. I'm going to use C and D, I guess. And this will give me CZ plus D. Okay, so things get a little weird here because I'm trying to get something. Okay, so we have CZ plus D, perform perspective division, and that gives me C plus D on Z. That's what I'm mapping to. Now I've got some conditions. I've got at the near, we want the image of that to be -1, I want to say. Yeah, I could have that wrong, but let's go with that. And then I could definitely have that wrong, but concept is still the same. So then at the far, we want that to map to 1. So let's put in those two conditions. So we have C plus D on N is -1. We'll call that equation 1. And then C plus D on far is equal to 1. Let's call that equation 2. Alright, so let's do process of elimination. If we take 2 minus 1, we have, well, C minus C. And factor out, so we have 1 on F minus 1 on N. Take common denominator. There we have it. Alrighty. Cool. And now what I want to do is I want to sub that into one of the other equations. Okay, so that was, what was equation 2 again? It was C plus D on far equals 1. Okay, and we have that D is equal to, okay, put that in. Basically divide D by F, and that gives us, and now we'll just go ahead and solve. There we have it. And so to sum it up, we have something like the following. We have that our projection matrix will be 1 on aspect times that tangent, and then 1 on the tangent, something like that. And as always, the devil's in the details, so there may have to be a correction factor involving basically the Z having to be swapped around. That might be -1 or something. But anyway, there we have it. So let's dive in and have a look at that in the code. Okay, so let's move now to look at the projection transform. So we'll go over to our header, and we're going to define a new function here. We'll declare. Alrighty, yep, I'm happy with that. It matches up with what we went through on paper. So let's go ahead and define that in our source file. I am a little bit of a perfectionist when it comes to formatting. It's a great way to waste an afternoon, is to worry about formatting, but I do like it. Okay, so first thing we're going to do is we are going to convert the field of view into radians, and we're actually going to take half of it. So if we were to go just like in the rotation code, field of view y times pi over 80, that would be the full angle. What we want to do is halve that again, so we'll actually just increase this denominator, double it, right? Double the denominator, halve the whole thing. So that is half of the field of view y in radians. I'm happy with that. And then I'm going to get a few of these things. So first of all, I'm going to get the tan value. I'm just going to call that t. And I'm also going to get the near and far, remembering to flip the z values around. And I mean, play around with this. It may be that I've got blinders on and I've missed some obvious thing, but I'm pretty sure this is correct. So we'll go ahead and build up our matrix. First thing I'm going to do is I'm going to write in a bunch of zeros. And I'm taking advantage of the fact that not every element needs to be overwritten with zeros, because, for instance, I know that the upper left entry of the matrix is a 1, or not a 1, but it's an expression which isn't 0. But we could just go 0 less than 16 would be perfectly fine. Cool. So now I'm just going to write in a few custom values as per the theory that we went through. I have just had a change of heart. Just for the purposes of numerical stability, I'm just going to write everything as zeros. Yeah, that's probably best. Okay, cool. Yeah, I'm happy with that. All right, cool. So, yeah, also important to note that I've switched this 1 over to a -1 in order to flip the Z value. Yeah, hopefully that works. Okay, so we'll just go back and we'll go through the usual dance. So we'll declare a uniform. Okay, and we will include that transformation. Great. And then we'll go right back to the main. And just the same as before, we'll get the location. And then we'll upload that directly. All right, so field of view Y will be 45 degrees. The aspect ratio will be the screen width divided by the screen height. The near distance will be 0.1. Anything closer than 0.1 will not be drawn. And anything further than 10 will not be drawn. Okay, cool. So, fingers crossed, let's find out. Remember, before we drew this and the far bits were being clipped, hopefully the position or perspective will be set correctly and everything will be visible. Let's give that a go. There we go. Now have a look. For one thing, these far points are not being clipped, but you'll also note that everything's gotten bigger, and that's because the camera was very close to the ground. It's taking perspective into consideration properly. So I'm just going to go ahead and close this, and I'm going to move the camera so that it's a little further away. There we go. Now let's give this a go. We should be seeing that the quad gets smaller. Yeah, and all of it is visible. Okay. So I'm happy with that. Now, just a side note, from this point on, I feel like I've really gone into a good level of detail on what uniforms are, how to declare them, how to fetch their locations and stuff. So I'm going to back off a little on that, all right? So unless it's super relevant, I'm not going to be going into as much detail on uniform stuff. Okay, so final bit. This is a bonus. So I know that I've gone through all of these matrices and constructed them. Hopefully we feel confident with them and we can see that really there's nothing special going on. We're just doing math. But there are benefits to using libraries which have been tested and so on and so on. So here we have the folder with the code. If we pop into the if we pop into the dependencies folder, we'll see that we have this GLM folder. I've included it. GLM is a header-only library collection, which basically, lets us do all of this stuff. And it's actually, Like this stuff is sort of janky. Like we can make it, but I've taken care to make it extra readable, and it's fine. It's fine. I'm not going to say bad stuff about my code, but let's go ahead and include this. So what we can do is we can, shame to see this go, we put a lot of work into it, but let's go ahead and delete the linear algebra stuff. Okay, and then we'll go to the config folder and we'll include this GLM stuff. So you see that actually I accidentally included GLM already. That's perfectly fine. So we have GLM that's good for definitions and things. We're also going to need to make transform matrices, and that's done with this GLM. I think that's it. We'll find out. And then I'm also going to need to send pointers to the matrices. So remember previously I was sending the matrix entries. The analog of that is what's called a value pointer. And we get that by GLM's module type pointer. Okay, excellent. So, yep, I'm happy with that. We'll head back, and now I'm going to sort of update all this code. So I'm just reading this top to bottom. I'm happy with this, happy with this. Okay, so this, all we need to do, because I've named this appropriately, is pretty much just, it's defined in the GLM namespace, the vec3 type. So we'll set those, get the locations. Yeah, I'm happy with that. Okay, so this will be a GLM mat4, and the GLM method is just called, yeah, it's just called look at. I'm going to need to define an up vector as well. That'll pretty much be doing the same thing as global up. So we go, what is it? Yeah, camera position, camera target that we're looking at, as well as the world's up vector. Okay, great. And we send that through. And now for this projection matrix, the method is called perspective, and it really doesn't change. I mean, I picked these conventions especially so that it would be easy to transition from one to the other, so no problem. Takes the same arguments, great. Now, as for these ones, this is a little trickier. So what I'm going to do is I'm going to create an identity, and then I'm going to keep stacking things onto that. So the way we create an identity matrix is if we create a matrix and we just put in a single number, then that number is inserted on the diagonals. So everything will be zeros, we'll have ones in the diagonal, that's the identity. Now what we'll do is, and this is, I'm just going to have my moment here, this is something which really bothers me, and that's the fact that this doesn't work the way matrix multiplication should work. So what we would typically do is rotate a point around the origin and then send it, like apply translation. But for some reason, just in GLM, it is the opposite. You would translate to a point and then apply rotation. That makes zero sense, but I'm sort of sick at the moment, so I don't have the energy to argue with it, but I don't like it. Anyway. So what I'm doing here is, well, first of all, anytime we apply any of these functions, we need to pass in the matrix, which that's going to be stacked onto. So this takes the original matrix, stacks on a translation, and we take the original matrix from here, stack on a rotation. We have the angle that we're rotating by. We're going to explicitly convert that to a float, because otherwise we get weird errors. And then the third argument here is the axis that we're rotating around. So yeah, there we have it. But yeah, we construct that, we upload it. Yeah, I'm happy with that. Right, but there's something I've missed, and that's in the upload, we need to, instead of going entries, we need to create a value pointer. So go GLM value pointer, and it's essentially, we can think of it as it's essentially getting a pointer to the entries in the matrix. Okay, so there we have it. Now, this is not going to be super satisfying because if we do it correctly, it'll pretty much look the same as before, but yeah, let's go ahead and do it. Unless we get an error. Yeah, I'm not above making errors. Okay, so just remove that header. We don't need that anymore. Give that another go. Oh, okay. Ah, right. Of course. We need to go back and modify the CMake because we don't have this source file anymore. Okay. Fun. Guess there are some benefits to IDEs, but look, there we have it. It is, yeah, I'm happy with that. Okay, yeah, so there we go. I know this is pretty long. This is a bit of an epic, but we went through converting between different coordinate systems. We did matrices from scratch. I hope you feel a lot more confident with them now if you weren't before. And we did all the legwork of making them all, but yeah, we can use libraries as well. All right, so as always, have a great one, and I'll see you again soon. Bye.